Now, can we test the correlation coefficient? What does that mean? Well, the usual thing. When we compute a correlation coefficient, we compute it from the data that we have available, and they come from a sample. So, can we extend whatever we find about the correlation coefficient from the sample to the whole population? In particular, how big should the correlation coefficient that we get in a sample be to indicate that there is a correlation in the population, to convince us that in fact that large correlation coefficient comes from the existence of a pattern in the population and it's not peculiar to our sample? Well, this is a bit of a tricky question, and here is another one where we need to be quite careful. Incidentally, I'm not going to talk too much in specificity about the specific tests that are done on R and what their RRSP conditions are, even though they are important in general. But in the case of correlation and regression, in fact, there is the bigger issue of linearity that and a couple of other major issues that are behind it. I think I'm going to focus on those ones. If you're interested in the RRSP features of the methods for testing R, please look them up on your own in the way that I've taught you. So, what should be careful about when we're testing R? Well, first of all the tests that are commonly used as a hypothesis test. Is it true that R is equal to 0? Okay, so basically all they ask is, can we assume from our data that the correlation coefficient is 0, or should we conclude that it is different from 0? It does not test, and they do not test whether the correlation coefficient is bigger than a certain number. Now, there are some tests that address that question, but once again, they're usually ignored. People always go back to this particular null hypothesis, which, as you can imagine, is pretty limited, right? So we're only asking, is the correlation coefficient 0 or not? So is there a relation or not? But we're not asking, is this correlation strong enough for our purposes? Now, this kind of tests always produce a p-value as usual, and the p-value can answer that question in the positive or the negative as usual. What does that mean? A low p-value suggests that R is not 0 in the population, which means that probably there is a correlation in the population. Okay? On the other hand, a large p-value suggests that there is no linear relationship, that we don't have enough evidence for a linear relationship, and the two variables in fact may not be linearly related. Once again, they may be related in some other way, but not linearly. But you also have to keep in mind some other things having to do with the interpretation of the p-value. Okay? For instance, there may be errors. Okay? The p-value may come out of a type 1 or a type 2 error. Our test may have too little power and therefore give us a type 2 error. Or we may end up with a type 1 error, so a significant p-value just by chance, and so on and so on. So let's have a look at a couple of situations where this can actually be detected and can be analyzed a little bit deeper. So when we're looking at the results of a test of the correlation coefficient, we may want to consider some other aspects of it. Okay? For instance, one thing that you may want to consider is the fact that we may have a small value of R showing up as significant. You may have an R value correlation coefficient of 0.1, say, okay, which doesn't look very big. Remember, these go on a scale of -1 to 1. So 0.1, you would think of it as being fairly close to 0, so indicating little or no relationship. And yet, that R value may generate a significant p-value. Why is that? Well, one of the reasons is because the same value of R can produce a lower p-value if it comes from a larger sample. Okay, so a larger sample, of course, has more power, so it may end up producing a smaller p-value. Okay. So in those situations, we may wonder, okay, this R value turns out to be significant, but is it really important for us? So this brings us back to the good old question or issue of the importance of looking at the clinical significance. Is a correlation coefficient of 0.1 really good enough for us to say anything of practical importance? Sometimes yes, sometimes no. The other issue that we want to look at is the fact that a small value of r, which turns out to be non-significant, may be caused by a nonlinear relation. Okay, so we may analyze the value of r, conclude that it's not significant, so we may end up with the wrong conclusion that, oh, there is no relationship between these two variables. Remember, this is not always correct. It's possible that two variables are related, just not linearly. So what you need to do is, once again, always look at the scatter plot. So never make strong conclusions. I would suggest never make any conclusions based on the correlation coefficient by itself. Always look at its value, at its p-value, and at the scatter plot, most importantly.